So just a bit of quick background. So I work with the big DOE climate model, E3SM, and specifically the high-resolution atmosphere component of it called EMEX-X. EMEX-X's goals are to have most of its code be C++ and to run an exascale. And so we are a heavy user of Kokkos. Around the 2019 timeframe, we had a need for a radiative flux code. And we found that this really good open source radiative flux code that was already out there called RRTMGP. But the problem is it's in Fortran and OpenACC. So what were our options? So first, you can write a C to Fortran bridge and just use it as it is. That minimizes the work, obviously, on our end. And obviously, we can just pull in their changes and use them right away. The problem, which I'm sure many of you know, is that OpenACC does not necessarily give you the performance portability that you need. And so we opted for a rewrite in C++. So the advantages and disadvantages are basically flipped there. So it took considerable dev effort to port. It's 10,000 lines of Fortran. And then obviously, if you want upstream changes, then you have to port those on top of what you already ported. And that led us to the next choice, which is how to pick a performance portability layer. So we evaluated Kokkos. At the time, HIP support was not yet in production, and there were some features that we really wanted. So we ended up rolling a new kernel launcher, yet another kernel launcher, also known as YAKL. It had HIP support, a simpler Fortran-like API with one-based indexing by default and automatic non-allocating arrays. Okay, so we made that decision. And then years go by, the code has served us well, but there is a cost to maintaining two kernel launchers. So first is code complexity, right? The rest of EMEX-X is in Kokkos, the radiation's in YAKL, so that means you need a Kokkos to YAKL translation layer, which was tedious. Also, there was an ongoing maintenance cost. So whenever we would update compilers or go to a new machine, YAKL had a way of kind of needing a little bit of coaxing to work, whereas Kokkos usually just worked. Obviously, Kokkos now has great HIP support. And probably the most important thing is that E3SM as a project kind of trusts and relies on Kokkos now. We have confidence in it that we didn't have a few years ago. So we've bought in. So can we transition to Kokkos as the one kernel launcher for E3SM C++ code? So we launched into this. There were several challenges. I've kind of tried to categorize them. So red would be a performance challenge, green would be correctness, and blue would be like more software engineering, software design challenge. So the radiation code does use temporary work views in a number of places. If you just allocate them like any other Kokkos view, the performance is quite bad. I'll talk more about that later. We got really lucky in that their usage and allocation pattern was quite simple. It was make a temporary view, call a kernel, call a function, whatever, and let the temporary view go out of scope. So I was able to basically roll a stack allocator, very super simple stack allocator, and that met the need and was very easy to write. We also hit some issues with MDRangePolicy, and so we ended up wrapping that with a macro, which I'll show you guys later. I made constant errors in the translation because of the 0 versus 1. Oftentimes it's trivial, but sometimes when you're doing arithmetic with indices, it's not. So at the end of every significant chunk of ported code, I had this validation layer. Basically, you do the YAKL, you do the Kokkos, you duplicate everything, and then you just compare, and they should exactly match. I wrote a special macro to measure and compare performance, and also did some increasing the generosity of the API. Okay, so I'm just going to walk you guys through the steps that I did real quick. So YAKL will be on the left, Kokkos will be on the right, and each slide will be a step in the transition. Okay, so there's a lot going on. I'll try to explain it all. So this is the example I picked. It's the long wave transport no-scat function. You could see it uses this simple bounds thing in YAKL, which is basically like a multi-dimensional range iterator. So they're iterating over 2 dimensions, NGDP and NCall. They're doing a downward propagation of radiation, and each layer depends on the one before it, so that first loop is serialized. The radiation interacts with the surface, and then it goes back up. You may notice that the indices and dimensions are inverted, so it's Ki at the simple bounds layer, but then it's Ik. That's because simple bounds always does a right iteration, and the data was hard coded to be the YAKL implementation was hard coded to be left. 3 minutes. Okay. If you look on the right there, you can see the Kokkos. For the most part, very similar. The MDRangePolicy is a little bit more difficult to use, but other than that, it wasn't really a problem. One thing I did do was to write an MDRangePolicy factory struct to kind of just make that a little bit more usable. I put a red box around the code that I changed. So that cleaned that up a little bit. And then I was able to template that factory on the layout. So unlike simple bounds, which is always layout right, the Kokkos MDRangePolicy can be layout left or layout right. So basically template it on the layout of the system, and then you don't have to do this dimension index inversion thing. And then here was a very important step. So here's the pool allocator. So I have kind of a contrived, this temp DN, basically just a contrived work view. And you can see I've replaced that with this pool allocator, and then you have to remember to deallocate it. And then here's the macro wrapper around the MD kernel. Allowed us to easily try throughout the whole system, try things like tinkering with MDRangePolicy, or even getting rid of MDRangePolicy and just manually flattening and unflattening the indices just in an inline function. So that had performance implications that I'll show. The next to last step was templatizing all of the view arguments. This allowed us to pass our EMXX, Kokkos field views directly into the radiation without having to worry about the layout or worrying about, it just worked. And then you pull out all the key types basically from the arguments that come in. And then finally, the timing macro. I put a red square around the right side. I didn't feel like taking another screenshot, but you put that exact same time macro, timed kernel around the YAKL parallel 4. And obviously it's around the Kokkos. So that allows you basically dump the function and the location of the kernel. You dump it to a file, and with some Python tooling, you can do comparisons. And then here's what it looks like actually calling this function. So you can see we've duplicated all the views. We call YAKL, we call Kokkos, we compare all wrap, basically making sure all the results are the same. And then we get to performance. I'll just go real quick. This was on Frontier. Okay, so without any improvements, this is what we saw. So this is a chart of how the 10 most expensive kernels compared when converted from YAKL to Kokkos. So 100% would be that the Kokkos performance matched exactly. You can see we're like 3.5 times. So without any improvements, we were way off. Okay, and here's with the pool allocator. So blue was the last slide, orange is the new, so you can see the change. So you can see just with the pool allocator, we went from 3.5 times to like 50%. So that was the big performance breakthrough. Yes. Oh, sorry. Do you see the red line with 100? Yeah. No, above is slower, and then below is faster. And so one thing I did notice, if you notice back here, some of the kernels, even though the overall time is much better, some of the kernels actually got a little bit slower. With a little bit of digging, I found it was because my stack allocator was not always giving cache-aligned memory, which had an impact on some of the kernels. Some of the kernels didn't care. So that got us a few percent better. Oops. That de-inversion of the indices also was a pattern that for some reason Kokkos just didn't like. So that got us an improvement on many of the kernels. And then just giving up on MDRangePolicy and just manual flattening actually improved most of the kernels. You see there was one big exception there. Yes. And so the very last step was basically custom tuning, basically that one kernel, just going back to what worked well for it. and maybe just a little bit of tweaking. And you can see now the bar is exactly at 100. And this is the final without any comparisons. So the total matched exactly. Some kernels were faster, some were significantly faster, some were a little bit slower, but the performance was right in the range that we wanted. So at that point, we declared victory.
Okay.
And
Thank you.
thanks. Thank you.